In open channel, the water flow is driven by gravity. The law of flow resistance are essentially the same as in closed pipes. In open channels, the calculation of the flow resistance are complicated by the existence of the free surface and the wide variety of possible cross-sectional shapes. The head loss over a distance L along the flow direction is given by the Darcy equation, in which the Darcy friction factor F is a function of the Reynolds number and the relative roughness, with Ks the equivalence on roughness height, which represent the height of the protrusion from the mean profile of the wall. The friction factor may be estimated graphically from the Moody diagram or in turbulent flow using the Colebrook-White formula. In gradually varied open channel flow, the Darcy equation may become an equation linking the velocity to the friction slope. And in turn, by rewriting, the Darcy equation may provide an expression of the friction slope. The friction slope being equal to the square of the velocity times a non-linear term. A seminal application is a main channel with adjacent floodplains. The shallow water zones, that is the floodplains, are usually much rougher than the river channel, and the bulk of the flow is primarily transported in the main channel, with the roughest shallow water zone acting as storage zone. The friction slope, however, of all portions must be the same. The following two photographs illustrate examples of floodplains in Taiwan, in Taichung County, and a river restoration in Japan, with partially inundated floodplain on the foreground. The total flow resistance may be estimated using the equation of conservation of mass, stating that the total discharge is the sum of the discharge on each of the sections. When the discharge, cross-sectional shape, and free surface elevation are known, the friction slope then can be deduced theoretically. A particular application is uniform equilibrium flow when the friction slope equals the bed slope. In this case, two practical applications of such calculation are: knowing the discharge, let us predict the flow depth in each section, and assuming a known water surface elevation, let us calculate the flood discharge in the entire cross-section. In practice, the complete hydraulic calculations are iterative. The following photograph on movies illustrate the January 2011 flood of the Brisbane River in Brisbane, Australia. The photograph shows a flood at Indooroopilly on the 12th of January afternoon, with the submerged overbank in the foreground and the main channel in the background. The first movie presents the Brisbane River flood in Toowong on the 13th of January morning, with the main channel on the left floodplain included the flooded avenue called Coronation Drive. The second movie shows the flooded campus of the University of Queensland in St. Lucia on the 12th of January afternoon. Note the complicated flow around the buildings, acting as large roughness element in the left floodplain.